So I'm going to start off today with a couple of questions that came in. Two of them actually that are related. One of them is asking what color is a mirror, and the other is asking, is that why, in reference to aluminum foil basically, marathoners get those reflective blanket things after the race? So last time I talked a lot about thermal radiation. I think I got bogged down in the details, but let me try to look back a little bit and try to pass off stuff that's ultimately useful. Wrapping yourself in aluminum foil or something equivalent to aluminum foil makes it very difficult for you to absorb or emit thermal radiation. Aluminum foil is pretty reflective across the entire electromagnetic spectrum. So it makes it hard for radio waves to get through. It reflects radio waves, it reflects microwaves, it reflects most of the other kinds of light. And eventually it starts having trouble in the X-rays and so on. But it's reflective. And so it's it's not good at absorbing light or emitting it as thermal radiation. So what comes off basically it reflects the light. And so as an experiment, next time you think of it, you got a chunk of aluminum foil in your hand, go open the freezer, if you got a freezer around, or face the cold outdoors, whatever, equivalently, so that you are radiating thermal radiation at the freezer much more intensely than it's radiating thermal radiation back at you. You'll feel cold, and it's not because you have cold air hitting you, and it's not because you're touching something cold and conducting heat. It's thermal radiation. You actually radiate hundreds of watts of thermal radiation. I figured this out at some point or other, and I forget. It is potentially hundreds of watts, and if nothing's sending it back because you're facing a very cold object, it sends something back, but not much. You'll feel cold because you're losing heat to the cold object. It's not sharing equally with you. Then put the aluminum foil between the two of you. What will happen then is you will radiate thermal radiation as before, but it will bounce off the aluminum foil and come back to you. You'll see your own reflection. You'll be exchanging thermal radiation with yourself. And the freezer will be exchanging thermal radiation with itself too. So it won't be receiving your heat anymore, and it will notice. It will stay colder. And you won't be sending off your thermal radiation unreplaced as much, and you'll feel warmer. So it's real. I'll talk more down the road about clothing and insulation in general. There are cases where you want to exchange heat easily, and a lot of cooking involves that. There are also cases where you want to prevent exchanging heat. When it's cold outside, which it is today, right, you're trying various strategies to keep from losing heat to the colder environment, because heat naturally flows from hotter to colder. And you do everything you can. One of the things is to introduce reflective surfaces. Wrap yourself up in something shiny. To respond to the question of what color is a mirror, the whole story of color and how we perceive it is itself a very interesting. It's both science and physiology, and I can, sometimes I do this, but I'm going to set that aside, but rather look at the. I do want to make sure I've left you with this. Some understanding of what it means to be a black surface or a non-black surface, and ultimately, so the color of a mirror, what color is it? Suppose we could see only red light. That is, instead of being able to see the whole rainbow spectrum, and actually the rainbow spectrum from Roy G. Biv, you probably learned at some point, from red working its way over to violet, that spectrum of colors, those are in effect the pure frequencies and wavelengths of light. The rainbow beautifully separates sunlight. Sunlight, which appears white to us, is a mishmash of many different wavelength frequencies of light. The details of wavelengths and frequencies you may have encountered before, but set them aside. They are distinguished in the way that a physicist sort of categorizes light, from red which is the lowest frequencies, longest wavelengths, over to violet, which is the shortest wavelength, highest frequencies. And if we pick one of those regions of the spectrum, red, suppose that's all we can see. Well, if you then illuminate something with red light, the red light will hit it, may or may not bounce off of it, and we will either see red light or less red light or no red light, and that will be our sense of color. We will identify an object that does not reflect any red light as being black. That's our sort of the classic definition of black, is a surface that doesn't reflect light. And if its red light comes back at us, we would say that's a red surface. It's able to bounce light. Actually, we might also call it a white surface. My strategy in trying to attack this is maybe not quite the perfect one at the moment, but if that's all we can see is red light, we either see it or we don't, and surfaces either reflect it or they don't, or something in between. Of course, we see more than just red light. We see a variety of colors, and let me stick with the red light for a second and say, what if you illuminate that surface with blue light, a different part of the spectrum? Well, it's this part of the spectrum we don't see anyway. So we look at it, we say it still looks black to us. We don't really know what that surface does with blue light, because we can't tell whether it's reflecting it or not, because we don't see blue light. Where I'm trying to go with this is, suppose we could see all colors of light. Yes, I thought I planned this strategy out. We actually can see the visible spectrum, right? Suppose we illuminate a surface with infrared light. Well, we can't see infrared light. We look at it, it's only illuminated with infrared light, it looks black to us. But really, we can't tell what the color is because we can't see infrared light, whether it's there or not there. We can't distinguish surfaces in that. So what I'm trying to do then is say that we can judge a surface's color only in the spectrum of portion of the electromagnetic spectrum that we can see and make an assessment. Does it reflect that light or not reflect that light? Returning to the real world of what we actually do see, we can look at a surface. If it's illuminated with white light, that is all the variety pack that we are capable of seeing, and if we look at it and all the light comes back off the surface, we would call that white. It's able to reflect all the colors of the visible light spectrum that we see. On the other hand, if it eats all the blue light, it absorbs the blue light, and none comes off, we would look at that and say, well, it doesn't reflect blue light. To our eyes, we'll see everything that's left over, which is going to be the reds and the greens and stuff like that. So we'll see that portion. We'll say that it's to blue light, it's absorbing. So we judge the color on what comes back off. Outside the spectrum, having mangled this, I'm going to make it short. Outside the spectrum that we can see, we can't judge color anymore. But suppose we actually could. Now, miraculously, we're able to see everything from radio waves all the way up to gamma rays. In that case, we would have a better sense of a surface's ability to reflect or either absorb or reflect all these wavelengths. If we saw a surface reflecting infrared light, so the infrared light comes in, bounces off, and we see it because we're now capable of seeing that, we would say that it's light colored or reflective of that infrared. On the other hand, if it was illuminated with infrared light and we saw nothing, we would say it's black in the infrared. And that's where I'm trying to go and didn't do my job right. And it turns out that most things in the infrared, as I was saying, are black in the infrared. Secretly they are. We can't tell it with our eyes. Machines can certainly see it. The exception in the infrared to all things absorbing it is the metallic, conductive, shiny things. So they, by and large, reflect the light the same way that aluminum foil reflects visible light. Do I want to say more about that? Okay, so the point being that most things are very good at emitting and absorbing infrared light, which is the thermal radiation of ordinary temperatures. So we're very good at exchanging thermal radiation. All right. Any questions about that? Sorry. I guess I can blame it on Friday. All right. I should make sure that, again, responding to what color is a mirror. The things that are poor at interacting with thermal radiation are certainly shiny surfaces that you look at and you say, that is a mirror. You see yourself, for example, in it. If this is the world of infrared, you would, in principle, see yourself reflected in infrared, but of course, your eyes aren't very good at seeing that. So that shiny surface, that kind of reflection is called a specular reflection because the light goes in, or the electromagnetic wave goes in, and it comes off at a very well-defined angle that depended on how it came in. So you get these mirror reflections that you see things in. You see images, you see yourself, you see reflections of some light source. So that's the simple mirrors. The other possibility is a surface that's highly reflective. That is, it sends the light back out. Every bit that comes in goes back out, but it loses the direction information. So you no longer see what the light source looked like. You can't see yourself anymore. And that's the world of white objects. So if you look at a sheet of paper, white paper, the light that went in, essentially all of it's coming off, and the copier paper will tell you what fraction of light it reflects. And they're very proud of it. It's 96% white or 98, whatever. Very good at sending light back out, but it totally loses the direction information. So all you get is this diffuse white. So shiny things, white things, both bad at interacting with light permanently. They don't absorb, they don't emit their own thermal radiation. And the last one is transparent things. If the electromagnetic waves go right through something, that something isn't very good at interacting with them. It doesn't absorb them. Well, if it doesn't absorb them, it doesn't emit them. So transparent materials are also don't emit or absorb thermal radiation. Okay? Let me leave that then. Is black body the same as black surface? A black body like a star or cloud? So thermal radiation, when I told you two things about, two features of thermal radiation, that the spectrum that comes off of a surface depends on its temperature. So as the temperature increases, the spectrum of electromagnetic waves shifts to higher frequency, shorter wavelength. So at very low temperatures, it's the world of radio waves. Medium, somewhat higher temperatures, microwaves. Higher still, infrared. Higher still, visible, and then on into the ultraviolets and so on. So that shift occurs. And the other thing is the brightness goes up dramatically with temperature, factor of absolute temperature to the fourth power. That story is told assuming that the surface is very good at emitting and absorbing its own thermal radiation, that it is in effect black. A black surface, a truly black surface to a physicist, is one that is completely good, perfectly good at absorbing light, absorbing electromagnetic waves, and consequently perfectly good at emitting its own thermal radiation. So there are ways of making a black surface, and the classic truly black, black surface is a hole in a gigantic room. So you get a huge room, huge box. It's all closed, and you make it already as black as you can inside that box, and then you cut a small hole. And this is it's the perfect black box. Why? Because if you send light into that box, into that hole, its chances of ever getting out again are zero. It's going to bounce around inside the box, and sooner or later something's going to absorb it. So any light that goes into the little hole is gone forever. So it's actually used in a laboratory. It's used in the laboratory as the black surface. It's just a blind alley for light, and it consequently emits thermal radiation as perfectly as possible. So if the temperature of the box is a certain temperature, that hole will be glowing away as perfectly as it can. So those are the ideal black surfaces, but there are many other black surfaces in the world. And what this is asking about is stars. The sun, believe it or not, is a jet black surface. It's as black can be, meaning that any electromagnetic wave that goes into the sun never comes out. It's gone, it's absorbed. And you might think, but it's bright, you know, what is it with it being black surface? It depends on your definition of black. If you want to define black as it doesn't have any light coming from it, okay, it's not black. But to a physicist, a black surface is one that absorbs all light. You shine the flashlight in, nothing comes back at you. And it meets that criterion. And because it's super good at absorbing light, it is also super good at emitting its own thermal radiation as that light. And so it's glowing like crazy. It's glowing as perfectly as it can. Well, and you know, what's perfection? It's pretty seriously black. And sunspots. If you cool down little regions of the sun, which happen, occasionally there'll be a place on the sun that's a little colder than the rest. Its spectrum shifts a little, and its brightness shifts. It gets less bright. So it's relatively speaking, it's darker than the rest. And so those are the sunspots. They're the cool spots on the sun's surface, and they start to look comparatively dark because, again, it's a black surface. It's just got a cold spot. Okay? Let me set aside then these heat transfer stories and go to a somewhat different topic, and that involves temperature and heat flow and that's the water, steam, and ice. So I picked this out as a way to look at temperature's effects on things that you deal with all the time, and water, steam, and ice are ones you do indeed deal with frequently. And let me get you thinking here for a second with a question. So here's a question. And suppose you've got a glass of ice water. So you have put ice and water in the glass, shaken it up a little bit, let it sit there for a while to make sure everything's all happy and settled. Compare the temperatures of the ice and the water. You okay with the question? Questions about the question? Let me get this guy going. Yeah, I'll give you 5 more seconds and then we'll call it. 3, 2, 1, 0. Yeah, they're the same. C. So it turns out you can have ice and you can have water at the same temperature. Temperature doesn't dictate one or the other, but there is an interesting relationship between temperature and those two phases of matter. And so that's the point of what I want to talk about today. So let's start off with ice, the issue of what ice is like. And actually, let me preface it. What I want to convey to you, you guys have dealt with ice and water and steam your whole lives. And what I want to add to your understanding of those things is the transitions between them. Those are the 3 classic phases of matter, the ways in which materials can exist. They can exist as gases, they can exist as liquids, they can exist as solids. You have some sense about solids have a fixed shape and volume, liquids have a fixed volume but not a fixed shape, and gases have none of them. They just can be any which way. But I want to talk about the transitions between the phases, why you have one and not the other, and the ways in which you can force one phase to convert into the other, and then things like there's a question on this relative humidity. What the heck is relative humidity? It's something that you deal with frequently, you might care about, it's the relative humidity, incidentally, of indoor air as the weather gets colder, gets lower and lower for good reason, reasons we can surely understand. And with that, things start drying out, you get chapped lips and all that stuff. So let's try to make it clear why those things happen. Okay, so the point of getting liquid nitrogen, yeah, I'm spilling it like crazy. I showed you, but I want to make sure you pay attention to it this time. Liquid nitrogen, when you pour it on the floor, which is always fun to do, it's like water on a hot skillet. It's boiling like crazy because as far as it's concerned, it's been put on the hottest ever thing surface, and it's just like crazy unhappy. And as it boils along, it lifts the little droplets off the ground on a layer of gas, and it scoops up all the dust. So these little balls rolling around, the hot skillet balls, are full of dust, and then when they dry out, they leave dust junk kicking around. Okay, so I got a little bit of liquid nitrogen into the container. Incidentally, this container, it's known as a dewar, D-E-W-A-R, like I think the beverage. It's trying not to allow thermal heat flow. It's doing everything it can to prevent heat flow. It's a double-walled container, so there's no direct conduction from outside to inside. Inside the double wall is vacuum, so there's really no conductive heat transfer through there. There's no convection because there's no gas inside the double wall to convect, and air that cools going down there becomes unbuoyant, right? It settles. There's no reason for the cold air to come out. So it accumulates cold air, and then the cold air sits there happy as a clam, and so convective heat transfer is all shut down. The only thing present is radiative heat transfer from the outer wall to the inner wall, and in a more complete dewar flask, that would be mirrored. It would have a metal mirror on the inside, so that there would be very little radiative thermal transfer from the outer wall to the inner wall. And so this building has jillions of properly made dewars, vacuumed, double wall, vacuumed, shiny metallized, and they keep cold stuff for a long time. Okay, so there it is, nice cold. And so a question I could ask you is, how cold is ice? Well, the point of doing this is the ice can be as cold as you like. It's a solid, and you're used to solids having various temperatures. Like if you go and on a really cold day and you go up to a big metal post somewhere that's been outside, it's really cold. It's way below freezing. This is why you do not lick it, right? It's cold enough it will freeze ice from your tongue really hard and cold, and you will, it's the mean trick to play on kids. Don't do it, okay? So this is an ice cube now that is at like minus, I should have zoomed in, but some of you can see up here. It is reading, I'll tell you, minus 30, minus 38. This is on a Celsius scale, so it's bitter cold. This is Alaska on a cold day. All right, so the point of this is ice can exist at any temperature you like down in the cold end. You can make it as cold as you like. But what if you start warming it up? And so suppose we put this ice cube and its buddies, and I will actually zoom in on the camera so you can see this. I'll plop it in because I can. Let me get the camera. This one will show you camera. There. And okay. So now you can see the thermometer. I need to bend the thermometer wire. So the water is currently at 19 Celsius. So it's above freezing. I put the really cold ice cube in there. I'll put some more ice cubes in there, and we'll let them sit for a while. And the question is, what temperature does it go to? And I'll predict the future. It's going to go to 0 Celsius. And that has everything to do with these phase transformations. In this case, the phase transformation between solid water, namely ice, and liquid water, namely water. The two of them right now are coexisting in that container, but they're not at equilibrium. And now it's a different word. I'm used the word equilibrium in a slightly different meaning from before. Up until now, equilibrium has meant zero net force, no acceleration. There's another kind of equilibrium. There are probably many of them, but physicists think of this as a thermal equilibrium. Thermal equilibrium is when two objects don't exchange heat. So they are not at thermal equilibrium yet, but they're getting there. So the ice, I can tell you, is actually colder right now than the water is. We're measuring the temperature of the water. It's harder to measure the temperature of the ice. Sometimes we've done this, but you freeze a thermometer inside the ice, but this is good enough. What's happening right now is that the ice is encountering water that's relatively warm, and the ice is melting. I mean, so far this is very familiar. You put ice in water, and the ice shrinks and the water grows. Microscopically, what does that mean? It means that at the surface of the ice cubes, and they're corresponding to the surface of the water near the ice cubes, there's an exchange of molecules. It's a busy place. Both of those surfaces, which are in effect touching each other, very busy, and I think of them like a busy airport with takeoffs and landings all the time. There are water molecules coming off the ice, entering the liquid, and that might be a takeoff, and they're doing the reverse, coming in from the liquid and landing on the ice and sticking. That might be a landing. So the exchange is happening all the time. Now, for a water molecule to break free of solid ice and enter the liquid, it takes some energy. Why? Because in ice, the water molecules are bonded together, not with full chemical bonds, where you really have to you'd have to get in there aggressively and tear them apart, but by pretty significant bonds of the same type I talked about in the wood stove. The idea that you bring two water molecules together, and they attract as you get to a certain point, and then eventually they start repelling. And if you let them touch and then you walk away, you will find they are stuck. So that's what happened in ice. The water molecules have stuck together by a deficit in energy, of chemical potential energy, that something has to repay to get them off. So even though the water molecules in water are still touching each other most of the time, they have less chemical potential energy. They're a little freer. They're not as strongly bonded to one another as they would be in ice. So the point is then that in order for the water molecules to break free of ice and go into the liquid phase, they need a little energy. And the energy that has to be paid off to turn solid ice into liquid water, it's known as a latent heat. You put the heat in, so that's the energy needed to melt some of the ice and turn it into liquid water. You put that heat in, and it doesn't change the temperature, it changes the phase. So that might seem a little odd that you can put heat into something and not cause its temperature to rise. But that's the case. The heat goes in instead into changing the material form of the substance. And so in this case, heat is coming out of the water, which was warmer when we started than it is now, and it was certainly warmer than the ice cubes. Heat was coming out of the water, going into the ice, which was colder, and facilitating the ice turning into liquid water. And the process involves water molecules taking off from the ice, entering the liquid phase. There is an ongoing return of water molecules back to the ice. It's in both directions. However, the takeoff process was winning. It's faster. There are more molecules leaving the ice than landing on the ice, and so the ice is shrinking in quantity, whereas the liquid water is growing in quantity. And where this should settle down, if physics is working, is at 0 Celsius. And why at 0 Celsius? What's special there? Well, the rate at which water molecules come off the ice depends really on how many are there at the surface ready to go, which is determined by ice's, basically its density. How many water molecules are there on the surface? It's not a flexible amount, it's a certain number, almost independent of anything you do to the ice. It's going to have a certain number in that much area. And the other thing it depends on is how likely it is that one of those water molecules, or each of those water molecules, will get the energy it needs to break free. And that's temperature dependent. At very low temperatures, in my liquid nitrogen-cooled ice, the chances of one of those water molecules finding enough thermal energy by chance, by statistics, to break free was basically 0. But as the temperature goes up, the chances of them breaking free gets more and more likely. So the rate at which water molecules are leaving the ice is temperature dependent. The rate at which water molecules land from the liquid water on the ice doesn't depend so much on temperature, because it's basically how many water molecules are in the liquid ready to stick times pretty much the chance that when one touches and lands, how likely is it to stick. And temperature doesn't have much effect on that. There's plenty of energy for it to do its job. It doesn't need extra heat or cooling, or it doesn't need heating to make that sticking rate change. So there will come a temperature at which the rate at which water molecules leave the ice for the water and the rate at which water molecules leave the water for the ice, they match. And that matching temperature is 0 Celsius. If you go below that temperature, it becomes unlikely that the water molecules will break free from the ice fast enough to make up for the landing, and you'll grow the ice. So if you cool the mixture down below 0 Celsius, the ice grows because landing outpaces leaving or takeoff. Okay? If you go above 0 Celsius, there's too much energy around, and water molecules break free from the ice too often. And the ice begins to lose molecules compared to the water, and the water grows. It's only right at 0 Celsius, and I'm sweeping a little bit of the details, pressures involved and stuff, but basically at 0 Celsius, the two of them can coexist in what's called phase equilibrium. You can have them both. And you can have them both, and they can be stable indefinitely. And that's where we are now. This should be reading 0, but it isn't, and that's just life. Okay? What this means that in my question that I asked you initially, I got another thermometer, I could try it too. When I asked you, the question is you put the ice and the water together in a container and you let them sit for a while. Which one's hotter than the other? Compare their temperatures. Well, not only are the temperatures the same, but we know the temperature. It's going to be 0 Celsius within a very small margin of error. And that's going to be true of any glass of ice water you've ever encountered, assuming that there's not other stuff in there. If you put other chemicals in and now you've mucked up the, you change the landing rate. If you put, I'm thinking of Dewar. If you pour whiskey into the water, okay, or gin or something, now you've got alcohol in there. You have diluted the water molecules. Oh, you're gonna incidentally, all these demonstrations, Al is responsible for these, so he's the guy to thank. So, yay! Yeah. And when I do stuff like leave the camera focused in on that he fixes the problem remotely sometimes. So I can't do. Okay, so we're going for 0. It should be at 0. Okay. Yeah. Thanks. Yeah. So if you dilute the water, you're going to suppress the landing rate, right? There's not enough water around it. An alcohol molecule is not going to stick. So you're going to make it harder for the water to return. You're going to force the ice to melt, because the rate at which water molecules come off the ice is unchanged. The rate at which they land from the water, the now diluted water on the ice, is slower. You're not going to, you can't sustain the ice because it's leaving faster than it's landing. okay? So you can predict how things will happen, okay? That's phase equilibrium between ice and water, and you can see how if you put extra heat into that system, what it will do is it will cause the ice to melt in favor of the liquid water. The temperature won't change, but you will have put the heat in that will drive more of this solid ice into the liquid phase. Your heat will go into what? It will go into the latent heat of melting. That is this heat that's involved in freeing the molecules from one another so they can become liquid rather than solid. So the latent heat of melting is significant. It takes a lot of heat to melt ice at 0 Celsius into water at 0 Celsius, which is part of why we use ice to cool things or keep things cold. That ice, to melt the ice, takes a rather stunning amount of thermal energy, even though it doesn't change the temperature of anything. Okay? Next, phase transition between water and its gaseous form, steam. Well, if you've got water around and an open surface above it, whatever that open surface is, you will have action at the surface of the water. You'll have water molecules leaving the liquid surface, having gathered enough energy to break free, and it's a lot of energy they need to get to break free. They will gather energy to break free and head off into the sky above that water surface. At the same time, if there are water molecules in the gaseous environment above the liquid, they'll land occasionally. So there's this, it's the airport again. There's takeoffs and landings at the surface of every portion of water you've ever encountered. Even surfaces that don't even appear wet, there's landing and leaving of water molecules all the time. We're just immersed in water coming and going. And the rate at which those two processes are occurring, the takeoffs and the landings, there are two different rates. If they happen to match for some reason, then the situation is stable. It's again phase equilibrium. You've got the landing and leaving matching, and so nothing's getting bigger at the expense of the other. But if, for example, the process of water taking off, what molecules taking off from a liquid surface is faster than the landing back onto the liquid surface, the liquid water will shrink. We call that evaporation. So you've seen this your whole life too. I should name the processes with water and ice. You know that if you've got water molecules leaving the ice faster than they're returning the ice, that's melting. And if it's the other direction, it's freezing. So those are transitions, melting and freezing transitions. Returning to liquid water and gaseous water, if the water phase is shrinking in favor of the gaseous phase, water molecules as a gas, steam or humidity, then you have evaporation. And if the water molecules are landing faster than they're leaving, that's condensation. So you've seen both of those, and you know water evaporates. You leave a cup of water out for a day and it's gone. Where'd it go? It went off to the gaseous phase. The landing rate was too slow. The leaving rate was too fast. It disappeared. On the other hand, in the bathroom, when you got cold surfaces and stuff like that, and you've been a steamy shower, where there's a lot of water molecules in the gas phase, they come and encounter all the cold surfaces and they land like crazy as compared to leaving, and they condense. And I told you earlier that it takes energy to break water molecules free of solid ice and turn them into liquid water, and that was a latent heat of melting. Similarly, there is a latent heat of evaporation. Well, sometimes it's called latent heat of vaporization. It doesn't, whatever name you like. And it's a huge latent heat. That is, the energy required to take liquid water molecules and break them apart and send them off on their way as gas is stunningly large. So this is why if you're trying to turn liquid water into gaseous water on the stovetop, it takes a while because it takes a huge amount of heat to break all those molecules free and send them off. But the same idea applies that when you put that heat in, that latent heat, when you're paying off the latent heat of evaporation, you can put a lot of heat into water, liquid water, and not have its temperature go up. The latent heat doesn't go into the temperature. It goes into breaking the molecules free and sending them on their way. Okay? There are two other phase transitions that I'll name and point out to you. They exist. And then I want to show you, I'll ask a question and show you a video. So here's, yeah, and I'll do some of the other demonstrations.
Well, yeah.
Yes. Okay, you get very close to zero. We got one of the thermometers reading zero exactly. The fancier thermometer, the one that's meant for scientists as opposed to just whatever. The other two phase transitions, they're actually between solid ice and gaseous steam. Oddly enough, you can go back and forth between those two without any liquid water around. And you have encountered these yourself, actually. When you have a surface of ice exposed to open space, water molecules occasionally break free from the ice and leave. And they become gaseous. And that process, zero, all zeros, it's good. Magic. So that process is known as sublimation, where ice just disappears into gas. You have seen this in snow, well, maybe in snow, just on a cold winter period where it snowed and the snow just sort of disappears. Where'd it go? That's one context in which you see sublimation. But the more familiar one is the freezer. In a frost-free freezer, which has very low humidity, which is a topic I'll come to, probably not today. The water molecules leave the ice in the freezer more often than they come back, and the ice disappears. So the consequences are, like the ice cube tray started off with full-size ice cubes, and after a month or two of inattention, they're like midget ice cubes. Where did they go? They sublimed. The water molecules just broke free and left. And it's also responsible for freezer burn. You put some delicious food out in the freezer, improperly wrapped, and all the water leaves, and now you've got like astronaut food. It's like, it's foamy stuff with no water left. They do use freeze drying. It is the process of freeze drying, and it's sometimes useful for things, but otherwise sometimes it just spoils your food. The reverse, where water molecules land out of the gas phase on the ice, is frost. It's actually, technically it's known as deposition, but you see it as frost on windows, for example. When the window gets very cold and humidity from the air inside the building just lands and sticks and becomes ice. Okay, so those are all the phase transitions. There's 6 of them. They all involve the landing, leaving processes being out of balance, and one of them is growing at the expense of the other. What I wanted to ask is this question. Quick question, and then fun and games, okay? Can liquid water be heated above its boiling temperature? And I haven't told you properly what boiling is, but it's an accelerated version of evaporation that has to do with evaporation into bubbles. So if you heat water, you're used to seeing water boil at a certain temperature with tremendous bubbling process, and it evaporates much more aggressively in that environment. And the temperature is hard to vary at that point. But can you vary it? So I'll give you 5 more seconds, and then I'll stop. 3, 2, 1, 0. Ooh, in favor of yes, 70%. Okay, so let's try it. So let me get this out of the way. What? Invalid entry? Oh, please don't do that to me. Open with.
From ABC News, this is Primetime Thursday.
We're going to start tonight with a report on something that you use every day, probably without thinking about it, the microwave. Tonight, we're going to show you how it can cause a dangerous explosion in your kitchen. This is actually a story suggested to us by one of you in a letter over the internet. And it involves a bizarre phenomenon. Before you use your microwave again, you really ought to see what Chris Cuomo found in this Primetime Owner's Manual.
At about this time last year, Patty and Dave Long of Naperville, Illinois, were preparing for Easter.
It was Good Friday. The kids were off school.
Time to make Jell-O Easter eggs. Patty put the water in the microwave for 3 minutes to boil, but something seemed wrong. No bubbles.
So I hit the add 30 seconds, and I stood and watched it. But it wasn't boiling, and I thought, well, you know, it's got to be boiling. Something has to be wrong.
Patty had been using a microwave for years. She was confused.
So I opened it up, I brought the container out, and I just kind of brought it down like this. So I was going to touch it with my right hand, and before I got my right hand there, I heard this like whoosh, and I got hit with all that water into my face.
It exploded.
It exploded like a bullet, and it just hit the ceiling too. There was no water left in the cup.
Patty had first and second degree burns all over her face. Even worse, the corneas of her eyes had been scalded.
The whole eye was burned, and they were swollen on the inside, so it was blocking some of the vision because of the swelling inside the eye from the heat.
Were you afraid that you may have gone blind?
Yeah, I was afraid I'd never see my kids again.
It would take 6 months of treatment for Patty to fully recover her sight. Still, no one could explain what had caused this accident.
It really wasn't until I got home and saw the water on the ceiling that I really understood that something strange had gone on here, something that I'd certainly never heard of before.
People who have these sorts of accidents are probably reluctant to talk about them because it seems so bizarre and so unlikely. Who would ever expect water, the safest thing we can imagine, to come up and hurt us?
Let us show you what happens in slow motion. Water heated past boiling, more than 212 degrees, can erupt. Mary Ann Ostermeyer says it happened to her, too. A middle school teacher in Southern California, she'd been using a microwave oven for nearly 20 years. She says she had been cooking homemade soup on low power for 50 minutes. Remember, low power.
Well, I ended up grabbing 2 hot pads. I opened up the microwave. I had one on the handle. I took and poured a small amount of soup in the cup. Then I reached in to the utensil drawer. I picked up a fork. By this time it was sitting down. I took the edge of the fork, or the tip of the fork, put it in, and the next thing I knew, there was this incredible sound like a gunshot or a backfiring of a car. And immediately there was an explosion. I mean, the whole thing just exploded.
What was the extent of the injuries?
First-degree burns on the face, first-degree burns on the wrist, and on the top section of the chest region. First degree, the lower quadrant of the left breast, third-degree burns.
Third-degree burns?
Yeah.
Both Mary Ann Ostermeyer and Patty Long's husband, David, searched for answers and found them here, a website by University of Virginia physicist Louis Bloomfield. It features video of an experiment that looked painfully familiar.
I probably get more questions about microwave ovens than all the other questions I get combined.
Professor Bloomfield says there's a simple scientific explanation for how these kinds of explosions can happen.
You're used to having water or liquid boil when you heat it above a certain temperature. But there are occasions, and they're more frequent than you'd expect, in a microwave oven where the water goes to or above boiling without any bubbles forming. That's a phenomenon known as superheating.
Superheating.
Yeah, it's hotter than it should be for normal boiling to occur, and yet it doesn't boil.
Here's why. Something has to start the bubbles forming. Any little imperfection, like the texture of a metal pot, will do.
But in a clean glass container, heated by a microwave, there's really nothing to trigger the bubble formation. It's a process that physicists call nucleation. That bubble formation never starts.
So Bloomfield says, even though it may look unheated, it can actually be superheated.
Now, what does that mean exactly if water's superheated? It's just hot? How's that dangerous?
Well, it's almost like a bomb once you've got it superheated adequately, because anything that triggers the boiling, once you've reached that temperature, will cause catastrophic, very sudden flash boiling.
Now, can you test this? Can we show it?
Well, we've got a container of about half a cup of water here with some red food dye in it and a little bit of fat floating on the surface, a little oil.
Like it were soup.
We microwave the liquid on high power for about 3 minutes. There isn't a flash reaction every time, but this can be dangerous. Don't try it at home. Look what happened to us.
Ready? Let's go.
Bloomfield says all it can take to trigger an explosion of superheated liquid is for something like a fork to break the surface. Then, watch out.
Is that? I got very good at superheating during that era, which, as you can tell, was a little while ago. But I got so good that I had to stop because the last time I did it was with a TV crew from Washington filming in our house. And in a single frame, at high repetition rate, in a single frame, the door blew open, hit me in the head, and the container blew completely empty. And on camera, there basically is this transition from we're watching, waiting for something, and then poof, me going, ah! So I stopped. Anyway, we'll talk about the physics of why that happens and really what boiling is on Monday.